Here we go. Now, lesson 33, matrix multiplication. We'll be able to multiply two matrices together. Now, before I even start this, let's be honest here. Matrix multiplication is perhaps the weirdest part of matrices. And although it's very odd and a very unique way to multiply two things together, it's actually pretty much the reason why matrices exist. The reason why we have these complicated rules for matrices and is because the matrix multiplication is so unique and it actually proves to be very, very useful. The other thing as well about matrix multiplication, a quick heads up, is that there is no matrix division. There are ways you can, I suppose, like undo a matrix multiplication, but there's no like idea of splitting a matrix up into parts. So there's not really the same idea of division as there is in regular numbers, but multiplication there is, and it requires a certain pattern. We're going to be doing a bunch of examples today, and we're going to be doing all these examples so that at the end you can be like, okay, I'm a little bit more competent, a little bit more confident as well in how to do these. But again, at the end of this, if you really don't understand how to do this, if you're sitting there and you're about, I reckon I could do it, but I think I need some help, I would strongly suggest taking 8 minutes of your life to watch the woman and Ed Rollo perform the same multiplications, and you can actually answer questions to check at the end to see if you actually understood what was explained. Before I talk about matrix multiplication, let's go back quickly to talk about what we did last time. Now, last lesson, when I was with you guys, we talked about adding and subtracting matrices. We talked about how addition of matrices have to be the same order. That means they have to be the same size. So you can add a matrix like this to a matrix like this, but you can't add it to one like this. Now you might even say, but look, there are 6 numbers here and there are 6 numbers here, but it doesn't matter. They have to be exactly the same shape in order for you to be able to add them. We also said that the other properties of adding and subtracting is that like they're commutative. It doesn't matter what order you do it. A plus B or B plus A are the same thing. Then once we did that, we said, well, and subtraction, by the way, of course, it doesn't matter as well. Subtraction is just going to be you subtract each element. How you do it is you add each individual element or you subtract each individual element. So for this one, what you do is you drop down both the matrices and then you draw a third matrix that is again the same size and you go element by element. 1 minus 1 is 0. 2 minus 4 is -2. 3 minus 2 is 1. 4 minus 3 is 1. That gives you your final matrix. And again, of course, you can't subtract B from C because they're different sizes. A 0 matrix means that every number in the matrix is 0, and they can be any size you want as long as all the numbers are 0. And the reason why they're powerful is because if I have 1, 2, 3, 4, and I add the 0 matrix, it's going to make a matrix that is 1, 2, 3, 4, because each of these elements is going to have 0 added to it. Really quickly, multiplying by a scalar is the last thing we did. We said when I multiply by a scalar, what I do is if I take, say, let's go with the 1, 5, 7, 9. Let's say I multiply this by 2. Each element gets multiplied by 2. So 1 gets multiplied by 2 gives 2. 5 gets multiplied by 2 gives 10. 2 gets multiplied by 7 gives 14. 2 gets multiplied by 9 gives 18. And that's done. It is a type of multiplication, but it's not the same as multiplying two matrices together. That's what we're going to do here. So first up, we're going to go through the rules. There are some rules about multiplying matrices, and these are pretty important rules. The first rule is matrix multiplication can only be done when the columns of the first matrix is the same as the rows in the second matrix. Now, obviously this is the formal rule. I'm going to show you the quick and easy way to remember that. The order of the resultant, of course, by the way, sorry, the order of the resultant matrix is the answer is the rows of the first by the columns in the second. Let's look at how, instead of using words, let's visually see what this rule looks like. If I have matrix A times matrix B, okay? And I'm using this dot as a matrix multiplier, and you'll see why. Let's say matrix A has the order 3 by 4. Okay, that means it's got 3 rows, 1, 2, 3, and 4 columns, 1, 2, 3, 4. And the rest of that's going to be just, And matrix B, well, matrix B is a 4 by 6. So it's got 1, 2, 3, 4, and then it's got 1, 2, 3, 4, 5, 6. And it's got, so it's a much larger matrix. But because these two numbers are in the middle are the same, the amount of, which means, what does that mean? It means the amount of rows here is the same as the amount of columns here. What that means is that this is now multipliable. So, and the resulting matrix, the final matrix, will have a 3 by 6 answer. It'll be 3 rows by 6 by 6, 3 rows by 6 columns. I know this is going to sound really, really weird, and I know this is going to, but I've been spending the past 4 weeks teaching genetics to my year 10 students, and I can't help but, because I've been doing that, I can't help but look at this and think to myself, it just reminds me of genetics. You know, the resultant baby daughter matrix gets 1 gene from its mom and 1 gene from its dad. That's not how you should think about it at all, but for some reason that's what I keep thinking about, is that it gets its column matrix, it gets its column identity from its mom, and it gets its row identity from its dad. Ultimately, you just, and you can sort of think it's like, oh, because they're multiplying. I don't know, whatever way you want to remember it. I think it's best to do it this way. It's best to just look at the middle two and see that it makes sense. Yeah, these are the random thoughts that pop into my head. You know what? As dumb as that thought may have been, it probably is going to make me remember it later on. But yeah, and it might do the same for you. Let's grab a quick look to check to see if we understand how to use these rules. Let's grab a look at these. Okay. Which of these are non-multipliable? Which of these can we not multiply? Okay, let's check here. So this one has a 2 and a 2. That will work. Tick. The resultant matrix will be a 2 by 4 matrix because it's getting a 2 from the start and a 4 from the end. This one, 3 and 2, they're not the same. This is not multipliable. Now 1 by 3 and a 3 by 1, hey, look at that. That is multipliable. These two numbers are the same. So we can now say, and the resultant matrix, by the way, will be a 1 by 1. It's getting a 1 from here and a 1 from here. A 4 by 2 and a 4 by 4. These are not the same, so therefore it's not multipliable. Now, the last one has a 1 and a 1. This matrix is going to be a big one. It's going to be a 5 by 4 matrix. So that at the end is going to be a pretty big matrix. But yeah, you're just looking at the last two numbers and the middle two numbers, check that they match. And if they do, you can just, you can do it. And so what that means as well, going back to our weird genetics idea of this, you can actually look at something like this. Let's just say I've got a resultant matrix, which is a 2 by 3 matrix. Okay. Now a 2 by 3 matrix could be made from taking the 2 by 3 matrix could be made by taking a 2 by 1 and multiplying it by a 1 by 3, because it's got a 2 and a 3. You can get the 2 from this matrix, and it can get the 3, but from that 3 can get from that one. But you could also get this same matrix by taking a 2 by 4 and multiplying it by a 4 by 3, or a 2 by 8 and multiplying it by an 8 by 3. And then in those cases, as long as this number in the middle is the same, sorry, I may have lagged there for a second. As long as this number in the middle is the same, it will create a 2 by 3. And that's because it can get the 2 from one side and the 3 from the other side. Now you can sort of see as well why I use this symbol, because I want to use this X symbol here to represent the order rather than to use this to multiply. There's another reason as well, which you may learn in university, because it's not taught in year 12, why we use the dot symbol for multiplication instead of the cross symbol. But yeah, don't worry about that now. Worry about that if you decide to do maths at university level. So, oh my God, I missed out on one of the most important rules here. Okay. I can't believe that. I'm gonna freehand it, I guess. Give me a second. I guess maybe I can talk about it later on. Do I talk about it later on? No, I don't. Oh my gosh, this is embarrassing. All right, hold on a sec. I'm going to do this. I'm going to do this. I'm going to do this. This is rule 2. And I'm just going to quickly talk about it now, even though I haven't got a proper slide for it. I can make a slide for it later on. And then when you get your slides, you can see how it works. The rule 2 is this, okay? Matrix that's the worst pencil I've ever drawn. Okay. Matrix multiplication is non-commutable. Now, I might talk about that later on anyway, but if not, I'm going to talk about it now. Let's just show what that means. Let's take matrix A and matrix B. Let's say matrix A is this matrix here. It's a 1, 2, 3, 8, 7, 6. It's a 2. This is a 2 by 3 matrix. Okay. And now let's take don't stress about it. Let's take matrix B. And let's say matrix B is a it's a 3 by 1 matrix. And we're going to put 11, 12, and 14 into that matrix. Well, oh, what the heck happened there? Oh, it's okay. I just went back 2 slides for some random reason. Now, this is a 3 by 1 matrix. Now let's check this. We're not going to do the matrix multiplication yet, but what I want to show you is this. If I took A times B, that would be a 2 by 3 multiplied by a 3 by 1, and the resultant matrix would be a 2x1 matrix. Okay, but now let's grab a look at this. What if I was to do B times A? Now, if I was to do B times A, I would have a 3x1 matrix, and I'm going to multiply that by a 2x3 matrix. But now, notice this number in the middle is not the same. This is not multipliable. And what that means for this algebra is that, and I'm going to write that here, A times B is not necessarily, doesn't have to be equal to B times A. Now, the reason why this is a big deal is because this completely is different from the way that we normally teach. This is completely different from the way that we teach other numbers. What do I mean by that? Well, in many other situations, multiplication is commutable. If I give you 3 times 2, that equals 6. If I give you 2 times 3, that also equals 6. It doesn't matter the order that these numbers are in, but in this one it does. Even if you could multiply A by B, it doesn't necessarily mean that they will be the same. A times B and B times A, you could still multiply them, but they may not be the same. The rule here is matrix multiplication is non-commutable. It is not always the same thing. It's actually very rarely that it is the same thing. So that's what the second rule is. Now let's actually do some matrix multiplication. How do you do that? Each element in a row is multiplied by the column in the other matrix. So how you do that is row 1 is multiplied by column 1. Then row 2, and the multiples are added and put in the resultant matrix, spot 1, column 1. How this works is it's called, most people, we call this the run along rows and dive along columns, or the run then dive method. Now, again, this is an example, this is best done with some examples. So we're going to do some examples on this, but ultimately I just want you to remember it goes rows first, then columns. You run from left to right, and then you dive. And yeah, and this work that we've done, calculating the resultant matrix, is actually going to really help us out. So let's do that now. Let's do our very first multiplication on A times B. So the A times B vector here, in this one, first thing we're going to do, I haven't given myself very much room here. We're going to do this first one here. We're going to check that it can be done first. This is a 3x2 matrix, and B is a 2x1 matrix. 2, 2. Firstly, that can be done. Now it's time to actually do it. The resultant matrix, by the way, is going to be a 3x1 matrix. So let's write this down here. Well, let's do it. I'm going to write it here. Go 5, 2, 4, 6, 1, 3. Then I've got a 8, 9. The resultant matrix is going to be a, what did I say? It was going to be a 3x1. So 3x1. And I'm actually going to make it wider than usual. You're going to see why in a sec. Okay, so first thing I'm going to do, I'm going to try and use as many colors as I can, is I'm going to multiply this row, right, by this column. So if I multiply that row by that column, I get 5 times 8. Okay, so and then I'm going to keep running along this column. So the next one that I run to is 2. 2 times the next one down in this column is 9. 2 times 9. Let's do this again so you guys can see where this is coming from. 5 is the first number in the first column. 8 is the first number in the first number in the first row in the first column. So I guess first number in the first row, first number in the first column. Second number in the first row, second number in the first column. I'm going a row and then I'm diving down. This is pretty easy for a one row matrix, but it will get a little bit complicated as time goes on. Hold on, let me question. Yeah. You can just, so someone's asked me the question, can you just write the answer down straight away? Yes, you can just write the answer down straight away. I'm just doing this fully so that people can see where these numbers are coming from. And yeah, so for the second one, you can skip some of these steps once you get, of course, when you do it yourself, but you should still, but I'm just showing you so you can see where they're coming from. For the second one, we're going to do 4 times 8. So first, second row times first column is 4 times 8. Second row, 6 times first column is times 9. It's going to be 6 times 9. I'm going to add those together. Okay, for the last one, we're multiplying for this one here, we've got the first 1 times 8, which is for the third row first number times the column, and then the third row second number times the column. And that gives us this big long mess here. Now it's just a matter of solving it. Now, you guys could, as I said, if you've skipped this first step, then maybe instead of this, you've already done these basic multiplications. So let's do them really quickly. We've got a 40 plus 18. We've got 4 times 8, which is 32, plus 6 times 9, which is 54. And then I've got 1 times 8, which is 8, plus 3 times 9, which is 27. Now, if you've done that, then it's all about adding those together, and that will give you the final matrix of 40 plus 8 is 58. 32 plus 54 is going to be 86. Unless I'm wrong. If I'm wrong here, guys, please correct me. 8 plus 27 is 35. Yeah. 35. And then that is now a multiplied matrix. Now, the trick here as well is to then say, well, it's a 1 by 3. This here is the product of the first row and the first column. This is a product of the second row and the first column. And this is the third row and the first column. That's where these numbers came from. Now again, so that's how we do it for the first one. Are there any questions on that so far? Okay, let's do now B times A. We're going to do that up here. Now, if I was to do B times A, what I'm doing is I'm taking a 2 by 1 and I'm multiplying it by a 3 by 2. Guys, can I multiply this first before I even start? Can I actually multiply this? Can someone tell me in chat or out loud? Ben says yes. Does everyone? How can we check? How can we check if it's multipliable? Do I need to unmute people? Can you not talk?
the column of the first matrix matches with the rows in the second matrix.
Yeah, so is that the case for this one here?
Wait, where?
I just changed the slide. Whoops. Is that the case for this one here? Is the rows, are the columns and the rows the same?
No.
No. These columns and rows are not the same. So the middle numbers need to match. The columns in the first matrix are not the same as the rows in the second matrix. So this one can't be multiplied. So we can just skip that one actually. For our last one we're going to do, this is going to be a bit of a doozy, so prepare, strap yourself in. We're going to do C times D. Now C is a 1/3 matrix. And D is a 3/1 matrix. Ooh, this is going to be interesting actually. So that means these two numbers are the same. We could actually do C times D or D times C. So that means that the resulting matrix is going to be a 1/1 matrix. So it's actually going to be pretty easy to do. Let's give this a crack now. We've got a matrix that is 2, 4, 7 multiplied by the matrix 8, 6, 5. And the resulting matrix is a 1/1 matrix. So it's, it's just going to be a 1/1. So let's do this. How would you do this one? Again, you go rows by columns. So row 1, we're going to start with number 2 and an 8. 2 times 8 plus, next one along is a 4 and a 6. Plus 4 times 6. The next one along, 7, 5. Plus 7 times 5. That is our 1/1 matrix. All we've got to do now is simplify that. 2 times 8, 16. 4 times 6 is 24. 7 times 5 is 35. That's going to be 40, 75. Where I go? And that's how I worked that out. That's going to be, 75. And that's a 1/1 matrix because that's what we would expect it to be. If I was to do DC, I'd actually expect to get, it should be a 3/, keep doing that, sorry. It should be a 3/1 multiplied by a 1/3. That'd be a pretty big answer because it's going to come out to be a 3/3 matrix. We're not going to do that matrix, but we could, unless you guys really want to, but I would like to skip it and just keep going on. Stop me now if you want me to go through it, but yeah, otherwise. Okay. I wanted to show you, I'm going to make this link available on the classroom later on, but I wanted to show you this. Some of you guys might find this, it's like a matrix hack. This is a way that you can multiply matrices without doing the same stuff that we just did. It's actually it's not what I would call a shortcut. It's just one of those different ways of oh my god, hold on. Yeah, it's just another way of doing it. Let me just pop this open. And it looks a bit nicer, and some people might be like, ooh, I like this method, but yeah. It's a TED Ed. I might see if I can skip to the actual important part. You all see the screen?
By now, I'm sure you know that in just about anything you do in life, you need numbers. In particular, though, some fields don't just need a few numbers, they need lots of them. How do you keep track of all those numbers? Well, mathematicians dating back as early as ancient China came up with a way to represent arrays of many numbers at once. Nowadays, we call such an array a matrix, and many of them hanging out together, matrices. Matrices are everywhere. They are all around us, even now in this very room. Sorry, let's get back on track. Matrices really are everywhere, though. They're used in business, economics, cryptography, physics, electronics, and computer graphics. One reason matrices are so cool is that we can pack so much information into them and then turn a huge series of different problems into one single problem. So, to use matrices, we need to learn how they work. It turns out you can treat matrices just like regular numbers. You can add them, subtract them, even multiply them. You can't divide them, but that's a rabbit hole of its own. Adding matrices is pretty simple. All you have to do is add the corresponding entries in the order they come. So the first entries get added together, the second entries, the third, all the way down. Of course, your matrices have to be the same size, but that's pretty intuitive anyway. You can also multiply the whole matrix by a number called a scalar. Just multiply every entry by that number. But wait, there's more. You can actually multiply one matrix by another matrix. It's not like adding them, though, where you do it entry by entry. It's more unique and pretty cool once you get the hang of it. Here's how it works. Let's say you have two matrices. Let's make both of them 2 by 2, meaning 2 rows by 2 columns. Write the first matrix to the left, and the second matrix goes next to it and translate it up a bit, kind of like we're making a table. The product we get when we multiply the matrices together will go right between them. We'll also draw some grid lines to help us along. Now, look at the first row of the first matrix and the first column of the second matrix. See how there's 2 numbers in each? Multiply the first number in the row by the first number in the column. 1 times 2 is 2. Now do the next ones. 3 times 3 is 9. Now add them up. 2 plus 9 is 11. Let's put that number in the top left position so that it matches up with the rows and columns we used to get it. See how that works? You can do the same thing to get the other entries. -4 plus 0 is -4. 4 plus -3 is 1. -8 plus 0 is -8. So, here's your answer. Not all that bad, is it?
The reason why I think this is actually not a nice sort of way to do this sort of problem is that it's sort of like like I don't usually teach it this way because it's just, it takes up a bit too much space on in the old textbook, in the old workbook, and it's obviously, I've done matrices enough times that I can be like, oh yeah, just go across and down, and then I sort of know what I'm doing. But the advantage of this one is exactly what he said. You can see where this comes from. So you can see, let me just draw on his actual work. You can see that this number 11 comes from this 1 and 3 and this 2 and 3. And when you start getting big matrices, you might start to be like, oh man, what makes up this spot? And you would say, oh, it's just this row and this column. There are some advantages to it. If you want to use this method, knock yourselves out, because I actually think it is a very valuable method. That's why I'm showing you. I just don't usually teach it myself. And why would I when this guy's got like such a soothing voice?
Just like with addition, your matrices have to be the right size. Look at these two matrices. 2 times 8 is 16. 3 times 4 is 12. 3 times... Wait a minute. There are no more rows in the second matrix. We ran out of room. So these matrices can't be multiplied. The number of columns in the first matrix has to be the same as the number of rows in the second matrix. As long as you're careful to match up your dimensions right, though, it's pretty easy. Understanding matrix multiplication is just the beginning, by the way. There's so much you can do with them. For example, let's say you want to encrypt a secret message.
And now we're going to stop, because now it's getting a bit off topic, but it's still interesting. I'm not saying it's not, but it's just a little bit off topic. Let's jump from there back to here. And then I'll pop open this, and then I'll quickly just see chat. There was a question someone wrote in chat that I missed, and I can't see it because I've got the wrong thing clicked. Geez, okay. Well, you know what? There it is. It's a bit laggy though. Sorry about that. I will chuck this link on to Compass if you want to watch it later in your own time. I think it's pretty good. It's just another method for doing it. Let's wrap up one more thing to this last thing, and this is actually going to be really good, as a point to finish off on, because not only is it a good point to end on, but it also gives us a chance to look at something when we have a bit more of a complicated answer. What about if you raise something to a power? Can you do that with matrices? Well, remember, a squared is exactly the same as saying a times a, which means that when we do a squared, what we're actually doing is we're actually doing 1341 multiplied by itself. 1341. Let's solve this together. And of course, a times this one is commutable. Doesn't matter which way you do it, you'll get the same answer because it's the same thing. But let's do this together. First thing, we know this is a 2 by 2. This is a 2 by 2. So the result will be a 2 by 2 matrix. Okay. You can only square, I think, certain matrices. You can only square matrices. Yeah, there we go. You can only and if you think about it, that should make sense to you, because if you try to square, you need to make sure the rows and the columns are the same. The only way for the rows and the columns to be the same, no matter which way you do it, is for them to be the same number. So you can 2 by 2, 3 by 3, 4 by 4, so on and so forth. So that means the result is going to be a 2 by 2 matrix. I'm going to give myself a fair bit of space though. You guys will learn very quickly. I've done this many times now to know that I'm going to need some space in order to solve this. So let's do this first one. I'm going to do in green the rows by the columns, the first row by the first column. That point's going to go here, top left. So 1 times 1 is going to be 1. And then 3 times 4 is going to give me 12. 1 plus 12. Okay, I could have done this. I might, yeah, I might, or no, I might do it properly actually. You know what? Let's do it properly. 1 times 1 plus 3 times 4. That means that I'm doing this by this. The next one is I'm going to do this point here. That is the first row, but it's now the second column. To do that, I'm going to go 1 times 3 plus 3 times 1. And of course, as I said, guys, if you want to take a shortcut here and just write the numbers down that you get, you can do that. I'm just trying to show people the full setup so that you guys can sort of see where these numbers have come from. Let's now do in purple this one, the bottom left. To do this one in the bottom left, we're going to use the bottom row and the first column. So that's going to be a 4 times 1, row, run, then dive, and then a 1 times 4, run, then dive, 1, 4. Then the last one is going to be pretty easy to do in red, is this one here. It's a 4 by 4, 4 times 4, and then, no, what am I doing? Ugh. Go away. 4 times 3, this is this one here. 4 times 3, and then a 1 times 1. Okay, that means that we're going to end up with, and I'm doing this really slowly, and some of you guys are probably like, oh my God, sir, you could just do this so quickly. And yeah, you know what, I could, but I'm just trying to show you guys where all this comes from, because someone might look back at this later on and be like, oh, I really want to know how he actually got that number. Then that's going to give you as a final matrix Okay, final matrix. 1 plus 12 is going to be 13. It's a different green. It's going to annoy me later on, but that's okay. 3 plus 3 is 6. 4 plus 4 is 8. And if I then do 12 plus 1, that's also 13. That is a squared. It's kind of one of the random things about a squared that I think is cool is that it actually doesn't have, it hasn't got 30, it's got 13. 13 is not a square number, but in this case, it is part of the square because this is how you made it. Now, as I said, if you want to skip to this step at the bottom, if you want to go straight from here to here, I actually, go nuts. It will be harder if you make a mistake to find out what you did wrong, but I've got no problems with that. That's just another way that you can solve this problem. If you want to go from instead, if you want to go maybe to here to this step straight away instead, that's another way you can do it as well. If you wanted to set this up as, if you wanted to set this up instead as they did it in that program, you could do it that way as well. You could do 1 3 4 1, 1 3 4 1, and then do it like that, and then use that. 1 times 1 is 1, 3 times 4 is 12, 1 plus 12 is 13, and then just do like this and just solve the rest of it as well. You could do it that way as well. Doesn't bother me which way you multiply them. Anyway, ladies and gents, that's everything about multiplying powers and how to multiply matrices in general. I hope that helped. I hope this made sense.